Hello, this is Dr. Michael Hassan, and this is lecture number 10, Karnaugh Maps, section 3, for chapter 3, Combinational Networks, for the course titled Digital Logic Design, or Digital Systems, or Digital Electronics. This slide is a disclaimer for you to read. There are many references in digital logic design. I cite 3 references. The chapter contents, we covered most important parts in K.map, Karnaugh maps. We talked last lecture about incompletely specified functions, complement of a function, canonical and standard form from the map, from K.map, and two-level implementations. We talked about 8 different two-level implementations for switching functions, including NAND and implementations. Today we will talk about plotting functions on the map. This is a very interesting topic. Design of multiple output combinational networks and variable dependent functions and map entered variables. And hopefully in the next lecture we'll talk about VHDL design too. Plotting functions on K.map. Plotting a Boolean switching function on K.map has many applications, including all Boolean algebra theorems and laws can be proved by plotting the right side and the left side of the law on maps and showing that they have the same K.map. Any two functions can be proven equal or not equal by plotting them on K.maps and showing that they have the same K.map or they do not in case they are not equal. We can perform any logical operation on two functions such as AND operation or operation exclusive OR by plotting the function to map in ANDing, ORing, and exclusive ORing the two maps by doing the operations on the ones and zeros which appear in corresponding positions on the two maps. So cell 0 with cell 0, cell 1 with cell 1, and so on and so forth. The ones and zeros which appear in corresponding positions on the two maps. The resultant map can be minimized to form the resultant algebraic functions produced by the operation. We can plot any function on a map to find all possible minimal and irredundant representations of that functions. We can plot any function on a map to find all canonical and standard forms for that function and its complement. We can plot any function on K.map to convert the function from sum of product to product of sum and vice versa. We can also plot any function on K.map to implement the function as a two-level network with 8 different implementations as we have seen it in the previous lecture. So what's the procedure of plotting functions on K.map? We identify the variables in the expression and the number of variables n. Once we know the number of variables, we can sketch the map, for example, 3-variable map, 4-variable map, and so on and so forth. Then we simplify the expression to one of two forms, a product of sums or sum of products, if the expression is given in other forms. We plot n-variable K.map, and for each product term, we identify its group of ones, zeros for each sum term, or ones for each product term, based on the row headings and the headings from the map. To cover a product term, we use non-complementary literals and complementary literals for the sum term. The sum term is the complement of the corresponding product term. As you remember, the max term is equal to the min term complement. The min term equals to the max term complement. This is example number 1 of a plotting function K.map. We are given f is equals to ABD or A bar, B bar, or C bar. Now we have the first term is ABD. The second term where we have 3 variables A, B, and D. The second term we have A and B as the switching variables, but the third term we have C. So this is clearly a 4-variable map. Since it is a 4-variable map, we will sketch a 4-variable map AB versus CD. AB, CD. We will put on the horizontal axis 0, 0, 0, 1, 0, which is the cyclic form of numbers. Then we have 0, 0, 0, 0, 1, 1, and 0. Now, how we have C prime? C prime is very easy. If you look at the C prime, if you look at the map, C will appear here. But we have this is C prime and this is C prime. So C prime will have a set of 8 ones because this will be C prime. D will cancel out. 0 will cancel with the 1. So I have this will be C prime. This will be 1 because C prime is C prime and 1. So I have a set of 8, group of 8 ones, okay, and I can refer this to C prime. So we are really doing the opposite to the minimization. We are trying to get actually the group from the term. So really this is like a reverse direction for re-engineering the problem, or reverse engineering the problem. Now, if we look at the second term, we have A prime, B prime. A prime, B prime is clearly here. I have this is A prime, B prime, and this is A prime, B, AB, and A, B prime. So A prime, B prime is here. Since it's the only one up here, so on the vertical axis I will have 1, so I will have a set of 4. So C prime generated a set of 8, and this will generate a set of 4, ones, and I can to indicate that this is A prime, B prime. Okay, now I have ABD. AB is 1, 1. And D is right here because D is 1 here, and so this 2 cells are D. So this is a set of 2. I will have A prime, ABD, ABD. So AB and D because D again, it is 1 here and it is 1 here. So this is the 2 cells, both of them are D, and this will be ABD. So once I have all the cells are not given, they are zeros. So I will label zeros. I will label them zeros. So the expression has 4 variables, hence we need 4 variable K.map as shown. The first product ABD is 1 when A equals to B equals to D is 1. We place 1s in the 2 cells, which are in the AB is A1 column and D1. Okay. The product term A prime B prime is 1 when AB is 0, 0, so we place 4 ones in the AB 0, 0 column. Finally, C is prime is 1 when C is 0. We place 8 ones in the 2 rows for C is 0. We duplicate the ones are not plotted since 1 over 1 is equals to 1. Okay, so we have all the ones, and the remaining cells will be zeros. Now, we identified the map. So once I identified the map, I can express the function f as a product of sums. To do that, I will group the zeros. We must look to find the product of sum expression as shown in the data groups of the figure, previous slide. We have 3 essential groups, S1, S2, and S3. The sum term is the complement of the product term, therefore the sum term S1. So if you look at the map again, S1, what S1 will look like? I have here A is 0, so it is 0, so it will become A or B prime, and the 1 will cancel the 0 for the D, C prime. So S1 will be, as stated here, S1 will be A or B prime or C prime, A or B prime or C prime, generated from column AB01 and C1 rows. We took the complement, always we took the complement when we deal with sum terms. The term S2 from the map S2, we have A prime. Just we complemented. A is 1, we take A prime, B, and here S2, the 1 will cancel with the 0 for the B, and C prime. Okay, so S2 clearly will be A prime or B or C prime. S3, the essential term S3, will come from those two. So this is the dotted line, so I have S3. The 0 will cancel with the 1 from B, so I have A prime, and or C prime or D, because C is 1 and D is 0, so C prime D. So this will be the sum term, and therefore the function f will be the product of the sum terms S1, S2, S3, which is A, B prime or C prime, and A prime or B or C prime, and A prime or C prime E. Now, given f, example 2 is AC or A prime, C prime, or BCD, and given f2 is equal to A prime C, AC prime, or A prime BD, I would like to express algebraically f1, f2, f1 or f2, and f1 and f2. Again, here we plot f1 and f2 on the map as shown in A and B, respectively, in the next figure. Then we will, so this is f1 and this is f2. We plotted those on the map. I will leave those for you as an exercise. So once those we have the OR, f1 or f2, we will OR each corresponding cells. So cell 0 or cell 0, 1 or 0 is 1. If we do this for every cell, okay, we'll end up with all ones. So really the F, the ORing of the 2 will generate 1. Function would be 1. And the AND will generate only 2 ones, and this will be F2, and F2 will be generated. So this will yield, so F1, F2 are shown, K.map for F3 generated by ORing the ones, as we said, and F3 will be 1. And F4 is generated by ANDing the ones, and F4 will be A prime BD. So if we read it, okay, so what we have A prime B and 0 cancel with the 1 for the C, so I have A prime BD, A prime BD. And this is very correct. Design of multiple-output combinational networks. The general design procedure for multi-output digital system can be summarized. I will have the design problem as stated. The number of systems input and output are identified and assigned letter symbols. The truth table that defines the relationship between the inputs and outputs is derived. The minimized Boolean expression for each output is derived using K.maps or other tools. The digital system is realized according to specification using all AND, all NOR, GA, ASIC, whatever the specification are considered. In this example, we have x3 to 8421 BCD converter. To do that, we have the truth table, ABCD. In x3, those are the inputs ABCD to the system, the outputs we call XYZ. So I have 0011 should give me 0000. Those 0 to 9 because those are binary coded decimal. And this is x3, which is corresponding to 3 to 12 in decimal. So once we will have one map for W, one map for X, one map for Y, and one map for Z. And if I plot, I will simplify the functions as we learned. So we'll have with W, X, Y, Z as shown here. And with all NAND implementation, I have AB goes to an AND gate, ACD goes to an AND gate, their output goes to an AND gate to give me W, and so on and so forth. I am X, Y, and Z. Now, if I have duplicated term, I don't have to use a gate again, just I will make really a connection to that output. So for instance, I don't have any duplicate terms here, so I don't have this problem. But in case if I have duplicate term, just I will have to make a connection from that term, so I don't have to do the gate again. Another example, we would like to design a 7-segment display. A 7-segment display, either common anode, which is here, or common cathode. If there's a common anode, I need a 0 to lit the light emitting diode. If it is a common cathode, I would need a 1 or plus 5 volt. So in case if WXYZ, this is a BCD, and this is the 7-segment. I have the 7-segment. Each segment is light emitting diode. So if I need to show a 0, I need 1 here in G, and all the others are zeros, because a 0 will give me light, right? So G has to be 1. And so on and so forth. So I have those. So I have a K.map for A, small b, small c, small d, small e, small f, small g. I will minimize, and I will get all these values as sum of products. Then I can implement with hardware. As you can see, we have a term which is a duplicate term. It's used twice, which is the term W x prime, y prime, z. It's used here in D, and it's used here in A. So I don't have to duplicate it, just I make a connection here from the output gate. And we implement it here with and or implementation. Now the next slide talks about variable dependent function and map intervariable. In a practice, it often occurs that for a particular combination, the function value may be neither 0, 1, or don't care. You remember we talked about don't care in incompletely specified function. So we have don't care, we have zeros and ones, that's very clear. But sometimes it is variable dependent, so it depends on a variable value of some external. These types of function called variable dependent function. Variables on the K.map are called map entered variables. Very simple. It's really an example. A function defined, I have 0, 0, 0, I have 1, 1 here, I have 2 don't cares. But those cells are dependent on the value of A. If A is 0, they will be zeros. If A is 1s, they will be 1s. And those will be dependent, those cells will be dependent on B's. So I can group them together separately. The B's, the A and the B are called map entered variables. And the function, basically the function of value V, we did not call it X, so we don't get confused with don't care X. So WV, YZ, what it will be? Those two ones, with those don't going to be a set of 4, and I have the 0 cancel for W, so I have D, and the 0 cancel will cancel the 1 for the Y, so I have Z prime. So I have the first term of VZ prime came from those two and those two as a set of 4. The set of 4 for the A, I will them, so I have the 0 will cancel with 1, so I will have V, 0 will cancel with the 1, I have Z. So I have VZ multiplied by the value of A. Because if A is 0, this will go away. If A is 1, it will be Z. So the function will variable dependent function depends on A. The same thing with the B. I have W B prime B. W B prime, this is everything will cancel on the vertical side. So on the horizontal side, I have W B prime multiplied by the variable, by the map entered variable B. So this is the answer that we have for the function. And this is called variable dependent functions and map entered variables. And this would be the last slide, and I would like to thank you so much. Please subscribe and see you soon. Sincerely, Dr. Hassan.